Okay, for problem number 4, using Gauss's law, calculate the electric field and electric potential inside and outside of a uniformly charged spherical shell with surface charge density and the uniform charge solid sphere with a volume charge density. Sketch the graph of the variation of electric field with radius and the variation of electric field with radius inside and outside of both A and B. So we're tasked to calculate for the electric field and the electric potential inside of this two problem or questions for problem 4. So for both spheres, for A and B, I already drawn a sphere which we're going to calculate later. So we're going to find its electric field and potential here inside of this sphere. It's either a spherical shell or a solid sphere. So for example, we have this spherical shell. Imagine that this probably might be an egg, for example. And this one, since it's a spherical shell, there's some electric field outside of this egg. We will calculate the electric field and its electric potential as well. And if we're referring to the solid sphere, probably it's a metal ball, solid metal ball, and we'll look at its electric field inside, as well as its electric potential, as well as its outer surface or outside of the solid metal sphere or solid sphere. We'll look at the electric field and its electric potential. Okay, so let us first solve for the charge of a uniformly charged spherical shell. We're going to calculate or look for its electric field. So let's go to this formula. Let's use this formula. Integral of the electric field inside is multiplied by the derivative, multiplied by dA is equal to Q enclosed all over epsilon naught. Okay, now what we're going to do is we have to put the area of this sphere. So have E in. So let's just omit first the vector or the arrowhead here, so that we can manipulate it easily. Multiplied by the area of the sphere, which is 4 pi area of the spherical shell, 4 pi r squared is equal to Q enclosed over epsilon naught. Next is, what we're going to do now is we should identify the Q enclosed inside the spherical shell. So if we try to take a look at this shell, we are calculating for the electric field inside. We know that there are no cavity or any opening in this shell, and also we have a free space here like an egg. Okay, therefore if this sphere is charged, therefore we can assume that there is no charge inside of this spherical shell. Since it's only a shell and there is an empty space here, you can predict that there is no charge inside. So therefore our Q enclosed is equal to 0. If Q enclosed is equal to 0, therefore the electric field inside will be equal to 0. Since if we substitute 0 here, you will end up 0 here. So if we try to cross multiply this one, 4 pi will go downward, it will be multiplied by epsilon naught, And if 4 pi epsilon r squared is multiplied by this value 0, your electric field inside will become 0. So let us try to solve next the electric field outside. So you have square root of electric field in outside multiplied by the dA is equal to Q enclosed all over epsilon naught. Okay, now what we're going to do now is as well same as here, we will remove first the arrowhead so that we can manipulate the equation easily. So E is equal E outside, the electric field outside is multiplied by the area of the spherical shell, 4 pi r squared. Now, since it is outside the spherical shell, and we say that according to the problem, the outside sphere or the spherical shell is charged, therefore the outside of this spherical shell can or impossibly become 0. Therefore the electric field outside has a value and it's not a 0. So let us calculate for that one. So let's separate epsilon naught to Q. So it's equal to 1 over epsilon naught Q enclosed. Recall that Q can also be equal to the integral of, so let us try to write it down, E outside multiplied by 4 pi r squared is equal to 1 over epsilon naught. Recall that the Q enclosed can be also equal to integral of Q and this symbol, the surface charge, multiplied by dA. Next, what will be the next is you have to get the integral of this one. So if we try to get the integral of this one, we'll end up with finding or evaluating these things, manipulating and cross multiplying this value here, will end up in this answer. E over 1 over 4 pi epsilon naught r squared Q. Okay. So if you're already an expert in electric or in math or in this field of electromagnetism, you can probably substitute and mathematically or mental math this problem. So we'll have to arrive at this equation. Okay, now for the potential of the spherical shell, the uniformly charged spherical shell, we'll calculate first the inside of it. So the electric potential of the inside of this sphere, let's assume that the radius inside is capital R and the radius outside is small r. So we will use these terms later if we are trying to solve for the potential of these spheres. So let us go to calculating the inside of the spherical shell. So we'll have Vn, the potential of the sphere inside is equal to the negative integral of R infinity, the electric field outside multiplied by dl minus the integral of R as capital R as it approaches the smaller r, electric field inside multiplied by dl. Okay, we try to analyze the equation from the outside, from the inside's value, the potential inside will be subtracted to the potential outside. So let us try to solve this one now. So next step that we're going to use is E can be equal to, or let's write this first, negative integral of R infinity approaches R. So we'll get the answer of Q over 4 pi epsilon naught R squared. Where did I get this value? You get this value from the first solving. You have this one, E out, which is 1 over 4 pi epsilon naught R squared Q, or you can multiply Q here to 1, so that you will have a numerator of Q minus the integral of R, capital R, as it approaches smaller r, or yeah, and the value for this one, for the inside, the electric field inside, the first calculations is 0. dl here is retained, dl. So if we manipulate this one, since this is 0, we will end up in the potential inside of the spherical shell into Q over 4 pi epsilon naught R squared. Here will be change. Sorry if I have this shortcut. So this will be retained. This will be 0. So dl can be equal to L, or you can change L to R. R. And if you cancel this out, you have to cancel this one as well as this one, and R can be changed into a bigger R. So we'll be arrive at this one. So this will be your potential. Okay, so now let us solve for the potential outside. Okay, so for the potential outside, we'll write this equation. The potential outside is equal to the integral of infinity R electric field outside times dl. Because why don't we need to put the subtraction, or yeah, subtraction, because on the first on the inside we're subtracting for this one up to the outside, but from the outside to infinity, from the outside cannot have any charge outside this outside, so probably we'll just have to deal with this outside only. Okay, so let's solve for this outside. So the integral of R infinity, sorry, I forgot, we have to put negative as well. We have Q all over 4 pi epsilon naught R squared. Again, the electric field outside. So what's next? The integral of this one will be V out is equal to, let's mental math this one. We call V out is equal to Q over 4 pi epsilon naught R for the outside. Okay, this is your potential outside. Okay, so let us now have the graph. The graph for the inside and outside of the electric field will become like this one. So we try to create a graph. Oops. So we have the electric field, also have the radius, since it wants to have the variation of electric field with radius. So our Q, the value that we get here will be put here. The value for the electric field on the outside. Remember that we have a value for the electric field outside, which is Q over 4 pi epsilon naught R, and our value for the inside is 0 if you try to recall our solving. And so let us try to graph this one. Supposedly this is your R. This is your capital R, the inside radius. So the inside radius has its graph is stay. It will stay because, like I said before, the electric field inside is 0, so it will stay or lay right here. Next, let us try to connect the inside from the outside. Okay, let's create a boundary here. Okay, if we try to graph this one, we'll have a sloping downward graph. Sloping downward graph. That's for the outside, the graph for the electric field. Next is the graph for the potential. Okay, so the graph for the potential V varies with the radius R. Okay, so if we try to get to look back at our equation in solving for the potential, they're almost like the same, but it will just stay. So for the first graph, for the inside, we get this value, Q over 4 pi epsilon naught R, and its graph, it stays here at the top. Okay, on the outer part or the outside of the shell, it will become just like the electric field, since the value for the electric field and the potential is looks like very the same, so it will go downward. So we'll have to put it downward. Okay, so this is the graph for the electric field and electric potential of the okay, so the next problem says here that we have a uniformly charged, this time this is a solid, it's not a shell anymore, so a solid sphere. So a solid sphere, if we try to charge the solid sphere, you try to charge this one, the inside of this sphere will be affected. It will also become charged. Therefore, if this sphere, the inside of this sphere is charged, therefore we will have a value, even though you don't have any cavity here. Since it's a solid, the electric charge will travel inside, unlike the spherical shell. It will not, since this the inside of the shell is empty space, while this the solid sphere is really a compact solid matter. So probably the electric field, the charge will travel along here since it's solid. And also we will solve for the outside charge and outside potential of the sphere. Yes, there is also a value for the electric field and electric potential of this solid sphere. So let us try to solve for the electric field inside of this solid uniformly charged solid sphere. So we have the integral of electric field inside multiplied by dt. Okay, since we're also looking for the volume charge, so yeah, we have volume. The previous one we have surface. So if we're using for volume, let's try using this symbol. So have is equal to Q enclosed over epsilon naught. So we will do the same process like we did on this left side. We try to remove the arrowhead so that we can manipulate the equation easily. Electric field inside, the same area of the sphere, 4 pi r squared. What else? We will try to separate epsilon naught from the charge or charge enclosed, and we'll have a symbol for rho, and we succeeded with separating. Okay, so the value for Q enclosed. Recall your formula, and also we'll try to manipulate this one. So you just cross multiply the 4 pi r squared here. We'll have a 1 over 4 pi epsilon naught r squared. This rho Q enclosed value can be equal to AR r squared over O in and 0 in, and we will have we'll have this equation, and finally we'll arrive at this one. En is equal to AR, this is A subscript R over 4 pi epsilon naught R cube. Okay. So if you try to take a look at this one, we'll just see that the electric field inside has a value. So let us now solve for the electric field outside. Your electric field outside, E out, will be can be solved using the integral of electric field outside multiplied by the dA equals Q enclosed over epsilon naught again, and again we will have this E out, electric field outside, multiplied by 4 pi r squared is equal to is equal to Q over epsilon naught. And then if we try to manipulate this one, you have to cross multiply your electric field outside. It will be equal to Q over 4 pi epsilon naught r squared. Okay, so now let us solve for another problem, or the continuation problem, which is the electric potential. So to solve for the electric potential of the inside of the sphere, we'll have to use the equation that we use for the electric potential on the spherical shell. It's just a formula anyway. So let us adopt that formula. We have V in, electric potential inside, negative integral of R infinity E out times dl minus integral of R and then R here outside, downward, and then E inside, electric field inside, multiplied by dl. Next is we'll have to substitute for the electric field that we calculated last time. So we'll have negative integral of R, here's infinity, and then our E outside is equal to Q over 4 pi epsilon naught R squared, if I'm not mistaken. And this is your E outside, electric field outside. Let's put dr or the dl. Substitute the assuming that dl is dr minus integral of r capital R qr over 4 pi epsilon naught R squared dr. Okay, next is we'll manipulate the equation that we substitute, the given that we substitute in the equation. So we have the same value like Q over 4 pi epsilon naught, and we'll be left with factoring this one to 1 over R raised to infinity, and plus 1 over 2R cube multiplied by, oh sorry, yeah, it's correct. And what else? When you try to derivative derivative of R here, we'll have R there, and you will cancel R on the top. We're left with single R, and if you factor this out, you will left with 1 over R. Your Q over 4 pi epsilon naught will be going out, will be put outside, since the cube over 4 pi epsilon naught here is also the same on the electric field inside. So let's go back. 1 over 2 R cubed R squared and R. Okay, and then how did we get this one? The derivative of R will have a dr, or if you get the derivative of R, you will have R squared, as well as having the R here. We'll add R in the down part. So next is we try to manipulate it again. Q over 4 pi epsilon naught 1 over R, substituting small r to bigger R to small r, plus 1 over 2R cube, and also have this one. And the potential here is R squared minus R squared, capital and minus. Next is to get Q over 4 pi epsilon naught. What should we do here? We will try to manipulate again. If you mental math this one, you get the the simplified formula for this one, you will get q over 4 pi epsilon naught and 1 over 2r multiplied by 3 minus r squared over r squared. So for the potential of the inside of the spherical solid solid sphere, you will get the potential, this potential. And finally, for the potential, so for probably for the outside, the potential outside is we have V out is equal to we'll have to use this formula again that we use on the spherical shell, but we were going to use it on the solid sphere. Negative of square root of r integral infinity electric field out times dl equals you have to substitute d out, the d out from the solid sphere, so we'll have integral of r, negative integral of r infinity q over 4 pi epsilon naught r squared. dl will become dr. So if dr will become r, the derivative of r is r, therefore we cancel the r on the denominator and the numerator. We're left with q over 4 pi epsilon naught r. So this is your V out. Okay, now let's try to graph the second sphere, this solid sphere. So we'll just create a graph here for the electric field with R. So according to our past calculations, our electric field in the solid sphere is A sub r and A sub r all over 4 pi epsilon naught r cubed, and our electric field outside is q over 4 pi epsilon naught r squared. So for example, we our constant electric field is q over 4 pi epsilon naught r squared. Will be starting here. Probably our E outside is around somewhere here, and our electric field inside is around we try to cancel out this one. It will become it will look like this one as well. It yeah, become just like this one. So they have the potential to become equal, since in electric field inside has a numerator of r and a denominator of r cubed. You can cancel r from the numerator and turn it into squared. So my graph for the electric field for the the electric field inside and outside will become this. Okay, this is the in and the out. While my graph for the potential, electric potential inside and outside, let's create a graph. This is V, this is R. If we try to recall our the final answer for potential inside, we have q over 4 pi epsilon naught epsilon naught times 1 over 2 over r 2r multiplied by 3 minus r squared over r squared. If we try to simplify this one, And our potential outside is Q over 4 pi epsilon naught R. It will become like this one. Let's try to put Q over 4 pi epsilon naught R here. If we try to graph this one, for me, it will become just like the potential on the spherical shell's graph. So we'll have this one. So inside and outside.